All right, so we're going to take a look at the second part of 5.1. So in the first part, we converted from polar to rectangular. That was the last thing we did. Now we're going to try the other way. We're going to go rectangular to polar. So when we start with a coordinate that's in the rectangular format, the one that we're used to using, all year, what are the two things called that they give you? X and Y. Yep. So now I'm going to give you the X and the Y. And when you write a coordinate in polar, what do we call the two things they?
Radius.
We need the radius and we need theta. Yep. So our goal is to turn an X and a Y into a radius and theta. So here's a point. Okay, that's on a rectangular grid. And the two things that you would know about that point, you would know, draw them in. You would know the distance from here to here. And what would we call that red line segment? Yep, that's going to be the X value. And you'd know the distance from here up to there. And what would we call that line segment? That would be the Y. Okay, and our goal is to figure out if we were to put that point on a circle, like this, I want to know how much rotation I would have to do to get up to right there. And I also want to know the size of that circle. So what would be the distance from there to there? That distance for that line segment in black, that's going to be my radius. And that angle right there, that's the amount of rotation between the x-axis and the hypotenuse to get to the point in blue. Okay. So our goal is to figure out the r and the theta. All right. Thank you. All right, let's start with the R. Okay. All set?
Yeah, thank you.
Yep, you're welcome. Okay, if you know two sides in a triangle, which we do, X and Y, what theorem can you use to get the third side? Yeah, you can use Pythagorean theorem. So x squared plus y squared equals r squared. All right, so yeah, we're going to use Pythagorean theorem. X squared plus y squared equals r squared. And I'm gonna write this down nice on the next page. Explain it, but that's basically where the formula is going to come from. We're finding the hypotenuse of a triangle. The next thing we're going to have to find is theta. So we're going to find theta, and we have to use the two pieces of information that we're given, the x and the y. What position is side x in relative to theta?
Adjacent.
It is adjacent to it. Yep. And what position is side y in relative to theta?
Opposite.
That is opposite. So to find theta, we need a trig function that has these two in it, opposite and adjacent. Cosine is adjacent over hypotenuse.
Tangent.
Tangent. Yep. So we're going to need tangent. We're going to fill in our argument, what we're plugging into the tangent. And that's going to equal a fraction. And what are we going to fill into the tangent function? Tangent of theta, it's always of an angle. And what would be my fraction on the other side? Y over x. Opposite over adjacent. Bless you. So that's the basic idea for how we get tangent, but that's not a formula for, that's how we get tangent theta. We need theta. So what do we have to do to get theta by itself?
Inverse tangent.
We are going to have to take the inverse tangent on both sides. So that's kind of a quick explanation where the formulas I'm about to write down are going to come from. But we're going to need inverse tangent y over x to get an angle, and we're going to need Pythagorean theorem to get the radius. So those two formulas will give me the two things I need in polar. All right, so the first thing we'll do is basically what I did on the other page. We're going to draw a diagram, and we're going to determine what quadrant the point is in. Okay, the quadrant is going to be important, because if you're in quadrants 1 or 4, you can use the exact formula that we just came up with. Inverse tangent of y over x. The problem with inverse tangent is inverse tangent, the way that that function works, will only give you an answer here and here. Inverse tangent would never give you an answer in the 2 quadrants on the left. But you can definitely have coordinates in the 2 quadrants on the left, so we need a way to get answers over here as well. Well, if you're in quadrants 2 or 3, you're still going to use inverse tangent y over x, but if you're in the upper left or the lower left, you have to add 180 to it. Okay. You only have to add 180 if what you're trying to convert is in quadrants 2 or 3. If you're doing it in radians, then you would add pi. Okay, I generally do it in degrees because we've talked about if you're going to get a nice answer to a problem, it's going to happen when you do it in degrees. So I would do it in degrees first, and then if I need to, I'll change to radians after by hand. Okay, so the top formula covers quadrants 1 and 4. The bottom formula covers quadrants 2 and 3. But where else can a point be besides in quadrants 1, 2, 3, or 4? Could be, well, it's always going to be on a circle. It's always going to be on some size circle, so it'll never be at the origin. But it could be on an axis. Now, think of like this point right here. If you were writing the coordinate of that point, what's the x value of that green point? The x value is 0. I don't know the y value, but the x value is, it could be 1, could be 2, depends on the size circle. But the x value is definitely 0. If you try to use one of these formulas and you plug in 0 for the x value, what would happen? Why not? You can't divide by 0. So if you try to plug in a 0, you're going to divide by 0, and those formulas don't work. So how do you do it if you're on an axis? Well, you just have to memorize the answer. When you're on an axis, it's one of 4 numbers: 0, 90, 180, or 270. 0, 90, 180, 270. And the same numbers we've used all year when we talk about rotation on a circle and we hit an axis. Okay, so now you've got a formula if your point lands in quadrants 1 and 4. You've got a formula if it lands in 2 and 3. And we know what to do if it lands on an axis. So that covers every possible situation you could have when you're trying to find theta. So the last thing we need, once we know theta, is r. So we have to find the size of the circle that we're on. And what theorem did we say a few minutes ago you used to do that? Pythagorean theorem. And that works no matter what quadrant you are in. So r squared equals x squared plus y squared. And that's the formula we wrote down right here. Okay, so converting between polar and rectangular, or rectangular to polar, no matter which way you're going, all you're really doing is working with a triangle and finding out information about a triangle. In this case, the information you're trying to figure out is the hypotenuse and the angle. All right, so let's try a couple problems where we convert from rectangular to polar. And then that will finish up 5.1. Okay, so we have the point 2, -2. So we know that's rectangular because they're telling us to change it to polar. So we only have 2 options. So that is rectangular. What are these two things called? The 2 and the negative 2? Yep, that's my x and y. And now, we're trying to figure out the radius and the theta. It doesn't matter which one you do first. Okay, so let's graph it. Where is 2, negative 2? That's 4. Write 2 down, 2. Right about there. Okay, we're not looking for an exact picture. We're just trying to figure out roughly the quadrant it's in. And what is your formula for theta when you're in the 4th quadrant?
Inverse tangent y over x.
Inverse tangent y over x. Our y is negative 2.
X is positive 2.
Generally, you can't switch those. In this problem, if you did switch them, you'd get the same answer, but that's only because they're both 2's. Well, one's positive, one's negative. When they're not the same, like, or opposite numbers, switching them would give you the wrong answer. So always put y in the top, x in the bottom. Okay, let's do inverse tangent of, what do you get when you divide negative 2 by 2? So I'm just going to do inverse tangent of negative 1, and I get a nice answer. I get negative 45 degrees. Now, if I had done that in radians, I would not have gotten a nice answer, and I would have gotten that. So if you want to get a nice answer, or if you want to have a chance at a nice answer, do it in degrees first. Does anyone remember what 45 degrees is in radians? Pi over 3 is 60. Pi over 4. So if you do it in degrees first, hopefully you recognize or you remember how to convert it. Multiply by pi, divide by 180. And pi over 4 is exactly, or negative pi over 4 is the number we just got.
Do you have to write it in radian?
It depends on what they ask for. So in this problem, I'll do both. Okay, so I'm going to do it in degrees first, and then I'll finish in radians. Okay, so I've got an angle. Now I need to find my radius. R squared equals x squared plus y squared. So r squared equals 2 squared plus negative 2 squared. Okay, so now I'm really finding the hypotenuse right there. That's 2, that's 2. All right, so when I do that, what's 2 squared plus negative 2 squared? 8, right? 4 plus 4. And to get r by itself, what do we have to do on both sides? Take the square root. So r is the square root of 8. Or when we reduce the square root of 8, what does that reduce to?
10.3.
So that would be if we rounded it. I just want to reduce it. I want to leave it exact, but reduce it.
2 on the outside, 2 on the inside.
Yep. So you can break up the square root of 8 into the square root of 4 times the square root of 2. Because 4 times 2 gives you 8. And then you can simplify that to 2. Okay, so that's when they ask you to simplify, they generally don't want you to round it, just reduce it. Okay, so 2 root 2. If they want you to round, then they'll say in the directions, round your answer to 2 decimal places. Okay. All right, so let's write our answer. So we've got the radius, bless you, and the angle. Radius, angle. Now, we looked at that yesterday. How many ways did we say you could write a point in polar?
4.
There's up to 4 different ways. That's one. Right? We could figure out all the 4 different ways, and that's what I had you guys do when I gave one of the examples and kind of walked around and checked in. But let's just do it one other way. So let's keep the radius positive, and let's make the angle positive. What would be the same angle as negative 45, but going around counterclockwise? Yep, 315. Just add 360 to it. Okay, so that is a second way you could write the answer. If the question didn't say a specific way, I would accept either one. But if it does say write your answer with a positive angle, then you need to make sure you change it to 315. All right, let's do one in radians. So 2 root 2, comma. What did we say 45 degrees was in radians? What is it? 45 degrees is pi over 4. So what's negative 45 degrees? Negative pi over 4. Okay, so technically that's not a different way. It's just this way repeated. I just changed degrees to radians. Okay, and let's do the bottom one. You can do that one in radians. So 2 root 2, comma. All right, and that one's a little bigger, so we might have to figure it out. Multiply by pi, divide by 180. Okay, if you did this in the radian mode on the calculator, you would get a decimal you wouldn't recognize. That's why we did it in the degree mode, and then we can change it ourselves and figure out what it is. What number divides into 315 and 180? Five. You could do 5. We would then have to do it another time. So it's actually a bigger number. 15, let's see, 270. Yeah, I think 15 does. So we could do 15. We're still gonna have to do it again though. But if you divide 315 by 15, you get 21. And if you divide 180 by 15, you get 12. So what number goes into both 21 and 12? 3. So if 15 goes in and 3 goes in, what number would have gone in originally? 45. 15 times 3. So 3 goes into 21 7 times. 3 goes into 12 4 times. So it's 7 pi over 4. And that's the answer we had right here, just changed to radians. Any question on that one? All right. So that's our first example, changing rectangular to polar, and let's try this one. Okay, this one is not going to work out as nice. So what we'll do is we'll round 2 decimal places. Okay, let's start with -4, -5. What quadrant is that? 3. 3. Oops. 3. Left and down. What's the formula to find theta when you're in the third quadrant? What did you say?
Pi plus inverse tangent.
Pi plus, okay, so if she said pi, we're going to use radians, which is fine. This problem didn't say. So pi plus the inverse tangent. And now it's important we get this fraction right. Y over x. -5 over -4. Okay, negatives will cancel out. And let's do inverse tangent of 5/4. I get that, and then I can add the pi after. I could have done it all in one step if I wanted. But that is an angle of 4.04 radians. Now, if you think, well, let's do it in degrees first to see if we get a nice answer, you won't. So if you do it in degrees, you type inverse tangent of 5/4. You get 51.34. And then if you add 180, well, it's still not a nice number. 231.34. But while I have that number, I can double check that that's right by multiplying that by pi and dividing it by 180. If I get 4.04, then I know we got it right because I did the same problem 2 different ways. So 4.04 is correct. All right, so that is the angle. And what would be the equation that I write down for the radius?
60 plus 20.
Um, yeah, so radius squared equals, and then when we do this plus that, you will get 16 plus, what did you say? 25. And when we add 16 and 25, we get how much? 41, and then take the square root. Since we rounded the angle to 2 decimal places, we might as well round the radius. If you wanted to leave the radius exact, that's the exact answer, the square root of 41. But if we do 2 decimals, we get 6.40. Okay, so one answer that we could write in polar is r, comma, theta. That's r, and that's my angle. Remember, the angle this time we did it in radians, but we checked it in degrees, and it came out the same. Whether you're in radian or degree, that would have no effect on this part of the problem. That's just Pythagorean theorem. The only part that radians or degrees affects is when you press a button like sine, cosine, or tangent. Then you have to be in the mode they tell you to be in, and on the test it'll say, write your answer in degrees or write your answer in radians. Okay, so any question on converting to polar from rectangular? Okay. So we've looked at what polar is. So now we're going to do a section from the back of the book on complex numbers. And then on Thursday, we're going to come back to polar and look at the connection between what we're going to learn in a minute, complex numbers, and what we learned yesterday, polar. So there's going to be a connection between section 5.1 and section A4. But we won't see that till Thursday. All right, so before we start section A4, I just want to look at a diagram that basically writes down the different kinds of numbers we work with, so we know the names as we start to use them. So we're going to start with this innermost box, and that's going to represent the simplest kind of numbers that you start learning. And each time we go out to another box, it's going to add more types of numbers into our system of numbers. What's the simplest kind of numbers that you ever started with when you started to learn about numbers? Or what's even the first thing you do with numbers? The very kind of probably like kindergarten level thing. Count, right? Count. So maybe even younger than that. But counting numbers. Okay, those are the simplest kind of numbers that we can have. And counting numbers don't include negatives. They don't include decimals or fractions. They only include numbers from 1 and out. And they go 1, 2, 3, 4, 5, 6, 7, things like that. Okay, so those are the simplest kind of numbers, counting. Once we start to learn to do arithmetic, we have a problem if we only use counting numbers. Right? With addition, we'd be okay. Right? If you give me a counting number, like somebody give me a counting number. 3. All right, and I heard 5. Well, if I take and add those 2 counting numbers together, no problem. I can always add 2 counting numbers together, and I'll get an answer that is a counting number. The problem would be if I made this subtraction. Right? If I took a counting number, which is 3, and I took another counting number, which somebody said 5, and I try to subtract them, I get something that's impossible with counting numbers. Right? I can't even do something like this with counting numbers. Because in counting numbers, there's no way to represent the idea of nothing. Okay? So if If you don't know how to represent nothing in math, then you can't do 3 minus 3. Right? So we have to expand counting numbers. Even though the next number we're going to introduce is not a number you ever use when you count. You never count 0, 1, 2. No, you never use this number when you're counting. But we need the number 0 when we start to do arithmetic. So whole numbers include everything that the counting numbers do, plus one extra number. That's the only difference. Whole numbers now include 0. So that solves this problem. I would no longer have to do 3 minus 3 and put a question mark because I don't have a way of writing nothing. I do have a way of writing nothing now. I write the number 0. Right. So now if we extend that a little more, let's take the same counting numbers a couple people said a minute ago. 3 minus 5. If we look at that, if I do 3 minus 5, would it be a number that is in the whole number system? No, because whole numbers only include things from 0 and up. 0, 1, 2, 3, 4, 5. So if I gave this to somebody, maybe in like first grade, they'd say, well, you can't do that. You're not allowed to take away more than you started with. Well, maybe if you only know whole numbers, but if you understand other kinds of numbers, you can take away more than you started with, and that gives you a negative number. Right? But not everybody knows about negative numbers when you start learning numbers. So that's the next set of numbers that we go to. So each time that we introduce a new set of numbers, we're doing it because we're trying to solve a calculation that has come up that we don't have a way of writing an answer for. Okay? If we don't have any way of writing an answer for that when you're in kindergarten, you don't know how to do it. So that you learn eventually about integers. Now, we could, with addition and subtraction, we're good now. Addition, subtraction, even multiplication. If you give me an integer, like -4, and you give me another integer, like somebody give me, what's another integer? 6. I can put an addition sign, a subtraction sign, or a multiplication sign. And I will always get an answer that's an integer. Okay? When you do -4 plus 6, -4 minus 6, -4 times 6. No problem. Where we run into an issue is if we try to do this. -4 divided by 6. Okay? Or even something simpler. Let's just take two positive numbers. 2 divided by 3. You can't take 2 and divide it by 3. Not in the integer system. Right? That'd be like if I said, here's two objects, and I want to give these equally to 3 people. Well, I can't. I only have 2. So how am I going to give these to 3 people? Well, the only way I can do that is if I start breaking these into pieces, right? Parts of things. And that's where rational numbers come in. So rational numbers allow us to solve kinds of problems where the answer isn't a nice number, right? It's a fraction or a part of a number. Okay? And rational numbers are used all the time. So maybe you're measuring something, and it comes out to 24 3/8 inches. It's not 24, it's not 25, it's 24 3/8. It's 3/8 of the next inch. When you buy something, it might not be exactly $25 or $26. It might be 57. So it's $25 and 57 hundredths, or 57 over 100 of the next dollar. So it's a fraction. And for most purposes, everyday math kind of stuff, rational numbers are probably as complicated as people need. But in math, we have more types of things we can do with numbers that would give us another question mark. We wouldn't know how to write the answer if we didn't expand it. And one of them is something like this. The idea of leaving a number like that. This doesn't exist in that system. Okay? But can we get square roots? Absolutely. We just looked at finding the hypotenuse in a triangle. And we had, I think the last problem was square root of 41, or we had square root of 8, or something like that. Well, you can get square roots in math. And one way you can get square roots is from the Pythagorean theorem. And there's many other ways, but that's one. So we need a way of saying, well, what is this? It doesn't fit into any system we know. So we're going to create a new kind of number called irrational. So now we're starting to get into numbers that are less everyday kind of use. They're not as familiar to a lot of people. Right? Square root of 2. So square roots, that's an irrational number. Okay, any square root that doesn't come out nice, like square root of 4, square root of 9, that's different. But square roots that don't come out nice are irrational. And that means there is no way you could write this as a fraction. Rational includes all the numbers that can be fractions. Irrational are all numbers that can't be. And if you think, well, maybe someday we'll figure out how to write the square root of 3 as a fraction. No, we won't. It's impossible. We can prove it's impossible. It doesn't matter how much time goes by, you will never be able to write the square root of 3 as a fraction. It can't be done. And there's another number we use a lot in math that is irrational. A lot of times we do it with circles and cylinders and spheres. Pi, yep. So pi is another irrational number. It's a number that goes on forever. There's no pattern to it. It's not like it's the same number repeating over and over, like 0.3. That's not irrational, 0.3 repeating. We can write that as 1/3. But pi is irrational. But I'd still say it's useful. I mean, a lot of people might use pi, like if you're doing anything with machining parts that have to be cylindrical or spherical or circular. You're going to probably use pi, or your computer program that's making the part for you. It's going to use pi to figure some things out about the part. All right, so now you take all the numbers that can be written as fractions, all the numbers that can't be, and that makes up what we call the set of real numbers. Right? That is what you do in Algebra 1, okay, the set of real numbers. But there's some more kind of calculations we can do, a little more complex than subtraction, a little more complicated than division, but it has to do with square roots. It has to do with the square root of a negative. Okay. Now, the applications for square roots of a negative, a lot more complicated than 3 minus 5. All right. When could you do 3 minus 5? Well, that's simple. You owe someone money. That's a common example of being negative. Like if you owe the bank money, you might think of that as a negative balance. You got to pay it back. Right? Breaking 2 things into 3 pieces, sure, maybe you're cooking. You got to take 2 cups of flour, break it into 3 pieces, and use 2 out of 3 of them, 2/3 of a cup. Right? That's pretty common. But square roots of negatives, those applications, those are much more advanced. You might see some in engineering. Right? Square root of a negative could come up, but right now there's no way to do that. Okay? If this kind of problem came up in whatever context you were doing, there's no way to write that answer. Okay? So right now in Algebra 1, you'd have to say, oh, we don't know. No solution. Can't do it. Well, if you're in Algebra 1, you might say no solution, but we have a way to do it. Right? I type it in on the calculator. The calculator gave me an error. And that's basically like what someone in Algebra 1 would say. You can't do it. Okay? But if I quickly teach the calculator Algebra 2, so now I just taught the entire course of Algebra 2 to the calculator, and I give it the same problem again. It doesn't tell me that it can't do it anymore. It gave me an answer because I allowed it to know about numbers that are not real numbers. And those are imaginary. So imaginary numbers extend the kind of things we can do in math to allow us to take square roots of negatives. And imaginaries also allow us to do other things. This class is not really a class where we look at applications of imaginary. We do a little bit of arithmetic, but that's it. We don't really do applications in this class. Now, if you take all the reals and all the imaginaries and put them all together, that's called the complex number system. And that's where we are right now. complex number system contains every kind of number that you've probably ever learned about in high school. Okay, so when you have a number in the complex system, it has two parts to it. Every complex number has a real part to it and an imaginary part. And that's what we're going to start with. So complex numbers are generally written just like I have on the board. A plus BI. A stands for the real part, that's in the left side of the diagram, and B is the number from the right side of the diagram, that's the imaginary part. When you write it in that order, just like that, 2 plus 3i is an example. That's called standard form. Could you write 3i plus 2? Well, technically, yeah, that's the same thing, but it's not standard form. So in the example that I wrote down, 2 is the real part, 3 is the imaginary part. Now, we haven't really talked about what this I is. Right now, I'm just telling you that the I stands for imaginary. We saw it come up on the calculator. The calculator used it. I'll talk a little bit more about what I means in a minute, but for now, just think of I meaning imaginary, and that whatever it's next to means it comes from the right side of this diagram. It comes from in here. Okay? If there's no I next to a number, then it comes from in here. That's the real part. Now, sometimes an imaginary number doesn't have a real part. Okay, the real part could be 0. So if a number doesn't have a real part, think of it like this. 0 plus 2i. If the real part is 0, we generally don't write it. We would just write 2i. That's called a pure imaginary number. It means that this part of the diagram over here is 0, and there's only a number from that part. So things like 4i, negative 2i, 0.6i. Those are all pure imaginary numbers. And we do the same thing all the time when there's no imaginary part. So in Algebra 1, I wouldn't write something like this. I'd probably just confuse people. They'd be like, why are you putting 0i? What's that mean? Well, in Algebra 1, we don't really need to know what 0i is. So all I would do is I would just write 2. Right? Anytime you write a number that has an imaginary part of 0, we usually leave it off. And we just put the real part, 2. Okay. Any questions on that? All right, so what does it mean for 2 complex numbers to be equal to each other? Well, let's say we had these 2 complex numbers. For the complex number on the left, a plus bi, what's the real part? A. That's the real part. For the other complex number, what's the real part there? C. All right, now back at the left one. For the one on the left, what's the imaginary part? That's the B. And for the one on the right, what's the imaginary part? D. For these 2 complex numbers to be equal to each other, basically, the real part has to equal the real part. So the A has to be the same as the C, and the B has to be the same as the D. Both parts have to match. So if I had a complex number like 3 plus 2i and 3 plus 8i, are those two complex numbers the same? No. And you might think, well, part of them are the same. Yeah, but they're not the same. For them to be the same number, both parts have to match. The 3 has to match the 3, and the 2 would have to match another 2. Like that. Those two complex numbers are the same. So it's a little different than real numbers. Usually when you're looking if two real numbers are the same, you just have to compare one number to one number. Well, here, you got to compare two numbers to two numbers. All right, so the next 4 things we're going to look at are add, subtract, multiply, and divide. Okay, we'll do add and subtract today, and then tomorrow we'll pick up with multiply and divide. So let's say we had to add those two complex numbers. The A, the B, the C, and the D, those will all be values when you do an actual problem. You can only think of it as like combining like terms. You can only combine real numbers with real numbers and imaginary with imaginary. So when you write the answer to this kind of problem, you look at the real part for the number on the left, look at the real part for the number on the right, and in this case, you're going to add the two parts together, the A and the C. Okay. Same thing with the imaginary. Imaginary part on the left is a B, imaginary part on the right is a D. And you're going to add them together, B plus D. And then make sure you put the I next to that, so we remember that the B plus D was imaginary. So it's like combining like terms. Let's try a couple examples. Okay, so we're going to add 3 plus 8i and 8 plus 2i. Okay, when we add those two together, what do you get for the real part? 11. Just the real part. Yep, 11. So we get a real part of 3, a real part of 8, and the directions say add them up. 3 plus 8 is 11. Because we're going to write a lot of things with i's in this section, I'm going to try to make my ones look definitely like a 1 and not an I. So we get 11. And what about when we add the imaginary part on the left to the imaginary part on the right? 10i. There you go. So 11 plus 10i. And that's all you can do. You can't add the 11 and the 10 and say, oh, it's like 21 or 21i. No, that's the final answer. Any question on that one? All right, let's try that one. So 4 minus 2i plus 3 minus 8i. How about the real part? 7. Yep, 4 plus 3. And how about the imaginary part?
Minus 10i.
Right, it's minus 10i. Okay, any question on that? All right, try one more. So this one is negative 3 minus 4i plus negative 7 plus 8i. Okay. Anyone think they could just give me the entire answer?
Negative 10 plus 4i.
Yep. So negative 3 plus negative 7. It's going to give me a negative 10. And then negative 4i plus 8i is 4i. So this is the kind of problem, you got to get the whole thing right. Like if you wrote negative 10 minus 4i. Even though you got the negative 10 right, you get the second part of the number wrong. It's kind of like if you meant to write 33, you put 32. Well, it's not the same number. Any question on that one? All right, so the last thing is difference. Difference is very similar to addition, except we're subtracting. So that negative sign that you see right here, think of it as being distributed. So you're going to do A, and then you're going to subtract the real part over here, C. Then you're going to take B and subtract the real part, that's D. So you have to, our imaginary part. So you have to subtract the C and subtract the D from the A and the B. Okay, let's try this one. 4 plus 12i minus 3 plus 4i. Jaden, what's going to be my real part there?
1.
Yep, 1. So 4 minus 3. And how about the imaginary part? What's that going to be? Yep.
8i.
Yep, 12i minus 4i gives you 8i. Okay, and one more. 3 minus 5i minus 8 minus 6i. Ruben, what's going to be the real part for that one?
Negative 5.
Yep. We got 3 minus 8 gives you negative 5. And Madison, how about the imaginary part? Negative 5i minus negative 6i. 1i. It's negative 5 minus minus 6. So that becomes negative 5 plus 6. So you can write 1i. Or when it's a 1, you could just write I. You don't have to put the 1. Right, if you put it, it's fine too. Okay. Any questions on that? All right, so we keep writing this I thing. Okay. Well, we have to kind of understand what that means. And to do that, I'm going to start with something else. What is that?
5.
Okay, can you tell me more about it?
It represents a number that doesn't matter.
It represents a number, right? But I thought that's a letter from the Greek alphabet. So is it a letter or is it a number?
It's a letter.
Well, yeah, it depends on what context you're looking at it in. In the Greek alphabet, it is a letter. It's a letter they use, like we use the letter Q. Right? It's a letter. But in math, we don't use that as a letter. When I go on the calculator and I type in that Greek letter and I hit enter, the calculator knows it's a number. It stands for the number 3.14. Right? So if we were doing like a problem in trig, we use Greek letters a lot to represent angles. Have I ever used pi to represent an angle that I don't know? No. I've used letters like alpha, beta, gamma, theta. I've used any of those. Those are fine. Because in math, these are all letters. This is not. In math, that is not a letter. It's the number 3.14. It's just a special symbol that means 3.14, so we don't have to write it up. This works the same way. Okay, I. When we're solving equations, like in Algebra 1, a lot of times you might see the letter X. You never would use I as the variable right there. Because I, in math, is not a variable. Just like pi is not a variable. That's a special symbol that stands for the number 3.14. I is just a special symbol that we use that stands for the square root of negative 1. Why do we use the symbol I? Well, it's shorter than writing a square root, a negative, and a 1. It's just a special symbol that means square root of negative 1. So if we're ever doing a word problem and you need to pick a variable, you can pick lots of different letters, especially if you're using an English letter. You have 26 of them to pick from, but there's a couple you don't want to pick. I is not a good letter to pick because it means something. Yeah, E is another one in math. O, the reason I wouldn't use O is because it kind of looks like a 0. So yeah, there's certain letters we want to avoid using, okay? And I is definitely one of them. So it says that I equals the square root of negative 1. Okay. Well, I can't really explain why that's true. It's just that that's what it is. If you want me to explain why that's true, it would be like you asking me why parallel lines don't cross.
Just doesn't happen.
It's just that's the way it is. That's the definition of parallel lines. Parallel lines don't cross. Why? Because that's how we define it. Right? Same thing here. I equals the square root of negative 1. Why? That's how we define it. Kind of think of that as like the building block. You got to start with something. And then off that, we can do other things. So what does I squared mean? If you write that out, let's say for someone who doesn't understand what that 2 means. Well, hold on to that. What-
Inverse?
So when you raise something to the second power, what does that mean to do?
Multiply by itself.
Multiply it by itself. So if somebody said to me, I don't get what the 2 means when it's up high, I'd say, well, it means to take the thing that's lower and multiply it by itself. It means I times I. And what did we just say I is equal to? It's equal to the square root of negative 1. So that's the square root of negative 1 times the square root of negative 1. What happens when you multiply 2 square roots together? They cancel each other out. Right? Like if I did, let's say, the square root of 9 times the square root of 9, that's like saying the square root of 9 to the second power. So this is like saying you're taking the square root of negative 1 and you're multiplying it by itself. Well, when you raise a square root to a square power, they cancel each other out. And what are you left with? You're left with negative 1. So even though we define I to be the square root of negative 1 and we can't explain why that's true, that's our starting point, I can show you why I squared is negative 1, and that's what I just did. So anytime we end up with an I squared in a problem, you have to change I squared to negative 1. Is that going to happen when you're adding and subtracting? No. When you're multiplying and dividing? Yes. Okay, we're going to get lots of I squareds. Okay, so remember that. That's important. I squared always changes to negative 1. If you leave I squared in the final answer, it's automatically not simplified. You haven't done the problem out.
But what if it was like 9i squared?
So if you had something like 9i squared, like that, I squared is negative 1. So you should be writing negative 9. 9 times I squared is negative 9. Yep, and that's the kind of stuff that we're going to see tomorrow. All right. So the homework for tonight, it's on 2 different pages. The first page is what we finished up with the polar and rectangular. That's 55 to 65 all. And page 560, that's the complex numbers that we just started, 9 to 14 all. Okay, so we'll look at that tomorrow, and then we will finish up A4, and we'll start our last section, but we won't finish it until first thing.